on the surface. Now, I'm going to illustrate with me what I'm about to do with the AFM head. Right? So what do I have here? So I'm the head. That thing up top, okay? It's got 4 legs. I only have, or 3 legs. I've only got 2, so it'll look a little funny. But my legs are the legs on that, right? My arm is the piezo. This is as far as I can move my arm. I can't move my arm down there. This is my rules. I can only move here, okay? I've now given it an amplitude that's 1, and I've given it a set point that's lower. When I tell this thing to engage, right here, the Z piezo extends all the way out. Why? Because I told it, make it 700 millivolts. It looks over here and says, well, I'm at a volt. The only way I can make that lower is to hit the surface harder. I need to be closer to the surface. So it puts it all the way to the surface. Can't reach it though, right? So the knob on the front, which is the one that's the slowest motion, I take that knob, which way is it? That way. I do it the right way, put the image in. So now it's reaching out, so now I'm going to go like this, and I'm lowering myself down. I look like an idiot, but you'll remember it, right? So I'm going to go down. Now, boom, beep, it beeps at me. I'm barely in range, but look, that's my total range. I don't want to stop right here. I want to keep going down until I'm halfway. Now if I run over a pit, I can go down into the pit. If I go over a valley, or a hill, I can go over the hill, right? The key thing is what I'm doing here is not engaging, I'm approaching. I'm bringing this big bulky head into range of the piezo on the surface, right? This is an approach. I'm bringing the AFM tip in range, okay? The engage turns on the feedback loop. If you separate those two in your head, engage is the piezo, approach are the wheels, then life is going to be simpler for you when you think about this in the future. Right? Okay, so now I got to come over here and do that for real. Now, first of all, I notice, oh, I'm a little out of focus here, so let me play with that, right? And I've still got this useless substrate now. It was useful before, now it's not useful. So I'm going to move all that over. So now I've got the right field of view, but now I need to adjust the focus. And remember that brass ring on that back column is what adjusts that. It's generally easy. I'm going to kill myself. So then, what I'm going to do, try to get that into focus. Now, why am I focusing on the tip and not the sample? Because the camera and the tip move together. The sample is fixed. So if I focus on the sample and start lowering the head, now nothing's in focus. Right? So I keep it on the tip. Now I'm engaged, or my engage is on, but I'm not in range. So I'm going to lower this down. Again, if I have this leveled the way I want it, if this is moving away from the middle, it means I'm tilting my head. So what I want to do is as I lower it, I want to lower them all together and keep that probe in the middle of the image. Now what you'll see is that if you have a reasonably reflective sample, you'll see a shadowing effect. Okay? And as you get closer to the surface, the shadowing is going to get closer and closer to the probe. That tells you you're getting closer and closer. Once you get very close, don't touch the back wheels anymore, because those move fast. The front leg moves slow. Slowly. That's English. As my daughter says, I talk English. My English is bad. So bring this down, bring that down, keep going. Now it's close. So now I don't want to move the back ones. I just want to move the front one. I want to be nice and gentle. If I just start torquing this thing and moving it all around, I've just blown my tip up, right? It doesn't matter if you're doing a coarse image, but if you're trying to do a nice image, that's going to be bad. Now it should beep at us. Let's see if it does. No, didn't beep. Oh, there it goes. Yeah, like 8 seconds later. Thanks, machine. It's not very helpful, but it does eventually beep. But now I'm on the surface, right? So I should be able to collect an image. However, right, this 1 volt 0.7, that was just to get the tip on the surface. I have no idea how rough this sample is. I don't know what the bandwidth of the lever is. There's a lot of things that I haven't really worked through yet. If I want an optimal image, I need to work through those things. I need to think about those things rather than just saying, okay, take an image and start messing with parameters in order to get something. So let's think about this logically, okay? There's really 4 criteria I want. Now that I'm in range, I'm just gonna hit stop, and now I'm gonna pull off the surface, and now it's just waiting. But the head is in range. The first thing I have to consider, how fast can I scan for any given number of pixels, right? Remember we talked about this during the talk. It's the mechanical bandwidth of the probe. The probe can't respond any faster than the resonance frequency divided by the Q. That's logical, right? Because it takes Q pumps to get it back up to equilibrium. As soon as you hit something and lose your equilibrium, if you go to the next spot before it has time to do Q pumps, you're not measuring that spot. You're just plowing through it, okay? Fortunately, I already tuned this lever so I can find what the resonance frequency and the Q are. Unfortunately, I can't get the software people to put it where you can see it, so you have to dig for it a little bit, okay? So I'm going to go into the tune that we were at before. My resonance frequency is 73 point, what does that say, 886, so 70, yeah. Let's just say 74 kilohertz. My Q factor is 158, so let's say 160, right? So I can bring up the Windows calculator, or I can use Igor's calculator. Igor is the software we live in, okay? Control J brings up the Igor thing, so I'll just use that. I'll type in print. I like to do it in kilohertz. You can do it in hertz if you want. Either way, it's fine. I'm going to type in 74 kilohertz. Divide its print 74 divided by the Q, which is 160-ish. So my bandwidth is 463 hertz. So the pixels can't come in faster than that. There's a really easy way to tell how fast the pixels are coming in. You go to Programming, Filter Panel, and there's a sample rate written at the bottom of that. That's how fast your pixels are coming in. So that's too fast. I have 400, I'm collecting at 600, right? This number needs to be smaller than this number, right? This is in kilohertz, so sorry about that. So go back to image. I either need fewer pixels or I need to scan slower. Either one will work fine, but I have to change one. Otherwise, I'm not getting an optimal image. So I'm just going to lower this down to 0.75. Now my rate dropped to 480, but I'm at 460. So let's drop that again. 440, 460. Now I'm below it. Good to go. All right, so that's one big question mark answer. How fast can I go? If I double the pixels, if I go to 512, I have to cut that in half again. Okay? Because it's the pixels per second that are coming in. Right? Now, again, I apologize on behalf of the moronic software people, you're recording that, right? That these two parameters are not visible, even though I've asked them to for about 4 years now. Right? It would be very helpful for it to be visible. Unfortunately, you have to dig a little bit, right? Even though it's a pain, don't neglect that, because your images will look like crap, right? I will show you guys that later. If you don't do this, you will not get a good image. There's no way, okay? So, again, you look on the tune, you find the resonance frequency divided by the Q, then you go to Programming, Filter Panel, and look for your sample rate. I usually take this and just kind of stick it down here, right, where I can see it. So even though it's covered up, I can always look and see what my sample rate is. It's a helpful thing to do. Okay, so that's the first one. The second one is, how big should my set point be? How big an amplitude should I tap with, right? If I'm imaging this feature right here, let me do it where you guys can see it. Let's say I'm imaging that feature right there with my hand, and I'm moving along like this. As soon as I hit that, I now have created a shear force on my cantilever. I have to walk up that, and my tip itself is not in contact with the surface. At some point, the tip will become in contact with the surface, but it'll do it chaotically. In other words, it's coming from the side, right? There is therefore a pretty good chance I will break my tip. If instead I'm tapping like this, then I will hit that feature in exactly the right way, because the feedback loop can detect it immediately and correct for it, unless you get extremely unlucky and barely catch the corner, right? So that's the second criteria. I need my amplitude set point in nanometers to be a realistic number. I have no idea how rough this sample is, right? So I don't know, so I have to guess. I don't know. I'm going to guess 100 nanometers. I might be wrong. I might break a tip, right? But then when I go back the second time, I know how big it is because I sacrificed the tip to figure it out, right? It's an iterative process. If you have an unknown sample, make a guess. If it doesn't break the tip, correct it and you're okay. If it breaks the tip, change the tip, start over again, right? But at least you're going to get the best possible image. So I'm going to guess 100 nanometers. Now, this is another thing that I would love to see here on the panel, but I can't get the software guys to put it. This one I understand because if you don't calibrate, then you're working with not real numbers. Again, though, we have to make the calculation. I apologize. I'll show you how to make the calculation. Try to remember it. It is in the manual, okay? And run this. How do you make the calculation? Well, you need the optical lever sensitivity, or more easily, the inverse optical lever sensitivity. I told you that this is a voltage, the set point, 700 millivolts. That's how much the laser is moving on the photodetector here, up and down, right? Right now, in free amplitude, it's about 1. I'm telling you a set point of 700. If I look over at the thermal tab where I calibrated, you'll look here and I'll see amplitude invols. Invols, inverse optical lever sensitivity. Okay, so again, thermal tab, invols, inverse optical lever sensitivity. What that tells me is how many nanometers I have for every volt of oscillation. Because it says amplitude invols. If it said deflection invols, that's slightly different. But amplitude invols is the nanometers that I get for any given volt. Right now I have it set at 0.7 volts. That means I take 0.7, multiply it by 148, right? That's my amplitude. Let's do the calculation. Control J brings it up, or you can do Windows Calculator. Print 0.7 times 148. 103 nanometers. There you go. I said I think my roughness is about 100 nanometers. My set point's at 103 nanometers. Maybe I'll give it a little more, right? But that's a reasonable number. In fact, I'm going to give it maybe 10% more, something like. I'm going to bring it up to say, let's just say 800 millivolts. So I know I have plenty of amplitude to get over the features, okay? So that brings us to the third criteria. Okay, so the first criteria is your imaging and with the bandwidth. Second criteria is that you're clearing the features on the surface. The third criteria is, we hinted at this in the talk, is that you're either in repulsive mode or attractive mode, depending on your preference and your sample, but not both. You cannot mode hop back and forth or you will destroy your tip and or your sample over time. Okay? So I'm in range. We made sure of that. I know what I want my set point to be. So now I just have to get the tip on the surface and make it force it into repulsive mode, right? Think about the tip as it comes down. As I come down, I get electrostatics, and then as I get really close to the surface, there's going to be a water layer. The water layer is going to wick up, and using capillary force is going to pull it down. Once I'm down on the surface, the only thing that's repulsive is how hard I hit. So that's my only knob. Hit harder. Is it in repulsive mode? No, hit harder. Is it in repulsive mode? No, hit harder. You just keep hitting harder until it gets in repulsive mode or until you have to adjust the amplitude higher to put more energy in it. But that's our one little knob for this. So what I'm going to do is I'm going to come over here and I'm going to tell it to engage again. The phase is either going to go up or down, or it's going to stay roughly the same. It went up slightly, right? It's up to 93. 90 is the free amplitude when you're above the surface. That's what the phase should be when you're off the surface. Once you're engaged, it's either going to go up or it's going to go down. It's a binary solution, sync function. If it's attractive mode, it's going to go up. Right now it's attractive mode because it went up a little bit. So now I have to hit harder. How do I hit harder? Well, I already decided what my set point is, so I can't lower my set point. If I lower my set point, I'm breaking my first rule, which is having an amplitude that's bigger than my features, whatever I think they are anyway. So that only leaves one option. I have to drive the tip harder. So now I go down to the drive amplitude. Everybody see that? I check that button next to it. I can come over to here, this little, we call it a hamster, because it's not a mouse, but it spins, right? Yeah, I know, bad. But now I'm going to increase the drive, and I'm going to watch this. When this phase flips over, I'm in repulsive mode. So then I've met my third criteria. Okay? So I'm going to increase that drive. Boom, it just flipped over to repulsive. Right? Typically, I want it to be between 60 and 80 degrees. That's a rule of thumb. That's not an ironclad rule. It's just a rule of thumb. In my experience, between 60 and 80 is stable. Above 80 is unstable. It's going to flip. You're going to get somewhere, it's going to flip, and then it's going to go out of control. Mixed mode will wear your tip out of control super fast. Repulsive mode is fairly steady. Attractive mode is really steady. Right? Attractive mode, it lasts a long time. The problem with attractive mode is it's hard to maintain, and over time you tend to mode hop, and it tends to degrade your tip. Okay? Alright, as your tip wears, you tend to move more and more to attractive mode. Okay, so now I'm imaging at the right speed. Well, not yet, but I've set the right speed. My amplitude is what I think is a good value. I'm in repulsive mode. I said there were 4 parameters. The last parameter is the gain. Right? I don't know what the gain needs to be right now because I don't know the sample. I don't know the optical sensitivity. I don't know any of that. I do know that you have an extended Z head. And I know that that's the blue stripe. You see the blue stripe on there? That means you have a 40 micron Z range, and the standard is 15. And so that means that the default value, again, you can thank the software people for this, is twice what it needs to be. So the next step is to set the integral gain to 5. Put it half of what the default is, because you have twice the range, so it has twice the effect. Okay? So start with 5. Right? Now I choose my scan size. Let's just do maybe 30 microns. Oh no, this is a 1 micron grading. Let's do 10. Okay? And now if I did everything, oh, I don't want 512, I want 256. Go back to that. I was changing that as an example. I don't want to wait that long. Okay? And because I'm in, sure.
I'm getting confused with the attractive mode and repulsive mode. I think you are teaching us on the tapping mode, right? Non-contact. Right?
No, it's not contact. It is contact. It's just that it's tapping. So that there was a misnomer years and years ago. Everybody was afraid of getting sued by Vico because Vico had a patent on tapping mode with phase, and everybody else was doing tapping mode with phase and stomping on their patent, but nobody wanted to admit it. And so people came up with these names: non-contact mode, intermittent contact mode, jumping mode, true non-contact mode. It's all bullshit, right? There's AC mode. It's tapping. You're either in attractive mode or in your repulsive mode.
So it is also contacting on the surface.
Oh, the only time you're not contacting on the surface is if you've got an amplitude that's maybe a half a nanometer, maybe 2 nanometers. Because in order to be in non-contact mode in ambient conditions, you have to be within the meniscus layer and not leaving the meniscus layer. Because as soon as you leave that meniscus layer, when you come back to the meniscus layer is going to create contact, right? So I know it really confused people for years because they made up all these stupid names that weren't real, right? But it's just AC mode and tapping mode, and that's what it is. Okay, so yeah, so I can make it be non-contact mode, but it's really hard, right? If you're in non-contact mode, you spent a good amount of effort making sure you were there. Does that make sense?
That means on attractive mode, you are pushing a little harder, and on repulsive mode, you are pushing harder.
Very hard, yeah. That's the key, and you can tell by the phase.
Yeah.
Some of the modes we do, like the really advanced nanomechanical modes, we actually push the phase all the way down to 40 because we want it to be coupled so firmly so that now you can extract spring constants and stuff like that. Here, all we're doing is trying to get an image, so we just want it a little bit in repulsive mode. Okay? After this, after I get the image and get through that, I'm going to walk you through a mental exercise to try to tell you why attractive and repulsive mode goes the way it goes. So it's like a macro scale exercise, mental exercise. But for now, I want to stick with this and do the image.
Yeah.
So the last criteria. So I said 4 criteria: scan speed, set point, attractive, repulsive, gain. I'm at the starting point of the gain, not the finishing point. I have to be imaging in order to figure out what the gain is. You can't figure out the gain without imaging or being a control theorist, which we're not. Okay, now I can close this. And yes, you can close it when you're on the surface, no problem. That's why that table, that active damper is in there, so you can move things around. Okay? So now I'm going to take an image. I can either do frame up or frame down, doesn't matter which. Frame up just starts at the top of the image, frame down starts at the bottom. Now, this should already look like a good image immediately off the bat, because I've taken care of almost everything. The only thing left is the gain. Now, if I'm imaging something that is absolutely critical and it's tiny and I need super high resolution, I don't want to overdrive the gain because I could damage my tip. If I'm just doing a routine measurement and I want the gain to be as high as possible to track, then I'm going to overdrive the gain. Now I'm going to show you how to overdrive the gain. But if you're doing nanoparticles, or if you're doing DNA, or proteins, or fiber, what are you doing? Fibrin. Yeah. You don't want to overdrive the gain because you damage your tip and you're not going to get high resolution images. I'm going to show you how to do it though. Okay? I'm just going to take this, make sure I'm on the gain. The outer wheel will adjust what you're changing. If you don't want to change the keyboard, you see the radio button, that's the little button, see it moving around?
Yeah.
I get on gain and I start driving this higher. And what you'll see is that the amplitude data will start to disappear. Do you see how much more data where there was here? It's white and dark and now it's just gray.
Yeah.
I'm actually improving the image. Okay? At some point, I'm still looking at the amplitude. You can't really see this in height. It's too subtle. But you can see it often in phase and you can see it in amplitude. Amplitude will show up the most. Okay? But as I roll this up, eventually, I'm going to go too high and it's going to start oscillating. I am now damaging my tip, possibly my sample. So I need to immediately drop that back down until it's stable again. If you're just imaging some sample and you want a step edge, or you want to measure some elastic modulus of a sample or something like that, that's probably no big deal. You can do that. If you're imaging something very delicate, don't do that. Just move it up until the image looks reasonable and stop. Okay? So again, 4 criteria. Scan speed, set point, repulsive attractive, gain. If you do those in that order every time, you will always get the optimal image. Right? Doesn't mean it's going to be a good image, but you'll get the optimal image for the system you have. Okay? Then we can change these color scales out because grayscale just sucks. You can't see it. So let's go mud. Helps a little bit. Actually, I like mocha. If you go in here, there's extra ones. 16 does a better job of this when I put that on there. But you can go into setup, and then you can choose mocha or whatever you want. I like mocha, and I like this.
Yeah, which one is your favorite?
Mocha.
Okay.
Yeah, it's better. It's a good lens. So let's see how.
Everything, but it's kind of
Yeah.
depends on something.
Yeah, like you see this dark and bright. It's kind of binary.
Yeah.
But if you choose the mocha, watch, it'll actually look better. Now you can actually see some gradation in between. Grayscale's terrible because it's a linear scale, and our eyes don't see linearly. So there's a mismatch there, and grayscale is really hard to interpret. I've had such situations where I was convinced that I had binary data, and I went to put it on a histogram, and it was not binary. It was just the grayscale fooling my eyes. It was a perfect Gaussian distribution, which means it was useless. But yeah. All right, so and then for phase, I generally like to use this Inferno. That's a decent color because it brings out the contrast. So what does this tell me? Well, one thing it tells me is that occasionally I'm actually mode hopping. You see the 90-degree bar here? Let me make this bigger so you guys can see it all the way around. You see that 90-degree? I'm occasionally jumping above it. So that tells me I need to hit a little bit harder. If I still hold that my set point is a good value, then I have to increase the drive. And now you can see still a little bit more. Now the highest it's getting is about 75, so that's good. So that should be good. Again, mode hopping is the worst thing you can do to your tip. It will wear it out. Okay? So then I can come back over here. See the little auto tile? If I want to re-establish those, I can just press auto tile and it'll reset them up.
What's happening here? Touching the surface?
That was the gain. That was the feedback error.
High
That's
gain.
when high gain. So you could see it very clearly in the amplitude, but you could also see it in the phase. And now what this is the difference between what my baseline phase was then and what it is now. If I just draw a box around that region right there and right click in the middle and hit fix scale, it'll redo that scale for the new scale. A lot of times people like to take the real-time adjustment. This is the master channel panel, and they like to set the real-time to flatten. And then what that'll do is that'll ignore any offsets that happen and make the data come in a little bit cleaner. Okay? So what does this mean? This means that on the flat parts, in between probably the contaminants, I have repulsive interaction. On these higher spots, because you can tell they're higher on the topography because they're brighter, I get a very strong attractive mode. Right? So I'm getting relatively repulsive on the flat regions, relatively attractive here. And you notice I didn't say anything about hard or soft, right? Because I really don't know if something is hard or soft. I only know that it's more attractive on the high parts and more repulsive on the low parts. Now you'll read papers out there that will say the phase went down or the phase went up, therefore it's hard or soft. That's not strictly speaking true. What it tells you is that the attractive or repulsive force changed. Now here's one thing that is true in general. If you have two surfaces that have the same charge, if it's more attractive on one than the other, then that one that has more attractive is probably softer. Because the tip is pushing further down in, you're getting more tip sample area, and you're getting more adhesion. However, if they have different charge, you can't say one is hard or one is soft, right? So you have to know the charge before you can say that. That being said, in general, brighter areas are usually softer. Higher, in other words, more attractive is generally softer. But you can't say that for sure without knowing the charge. Okay? Now I can go back and say, all right, well, I made these assumptions about the height being 100 nanometers. Maybe this isn't 100 nanometers. So let me look at this. Now right now it's giving me some ridiculous offset of -3 microns or something like that, right? That's not very helpful. So I want to flatten that line out and see it a little better. So what I'll do is I will look back over here at the master channel panel, and I want to hit setup, and I want to show this auto thing here. If I uncheck that, then it's going to level that out, or not. Oh, that's the phase. So now that's flattened that out, and I see what the actual amplitude is. I can even roll up this to see. And actually that wasn't a bad assumption. These particles are about 40 nanometers. So although I'm probably hitting a little bit too hard with 100 nanometers, right? It's better than not it's better than not being able to clear the particles. So I would consider this to be fine, right? If this was 2 nanometers, I would probably want to lower the set point back down and lower the drive back down, right? But that's a concept you want to get in your head, is that when your drive and your set point should always kind of move together. If you want to hit harder, then you drive harder for any given set point, right? If you want to hit softer, you drive less for any given set point. If you can't get it in repulsive mode, then you start with a bigger set point and then drive harder. Because the bigger the set point, the more energy is in the system overall. Once you've chosen a set point, you adjust the drive to get it into repulsive mode or attractive mode, right? That's always the order of things. At first it's going to seem a little counterintuitive, but as you use it more and more, if you're thinking that way in terms of set point based imaging, you're going to be better off and you're going to get better images. Is everybody confused, or did that make sense? Everybody's confused. All right, we'll go over it. We can talk a little bit more about it again later. But I understand the steps, right? Choose a set point. What was the next one? Get it into repulsive. What's that? Oh, it's scan rate. Scan rate, set point, repulsive, and then the gain. If you follow those steps, you're going to be fine. Properly. Okay? Now, imaging, right? Somebody has on here PH2, which is a bit weird. Let's just put, I'll just put CAL for calibration. I generally put an underscore at the end of the base name. As the system collects images, by default, it saves an image every time it finishes a frame, provided you don't change something big like scan size, or it'll save for scan rate. Scan size or offset or scan direction, things like that, it won't save it, it'll wait. And every time it finishes, it increases the suffix at the end. So if you're running an experiment on graphene, then you would probably name it graphene underscore or whatever treatment you did. And then if you took 10 images, it would be graphene 0, graphene 1, graphene 2. By default, the system saves the data in a directory in My Documents, Asylum Research Data, and then today's date, written in the European form. So, for example, today would be 2019-130 or whatever it is. I don't remember what today is. Is it the 30th? 29th. 29th. Okay? If you leave the software open and walk away and come back tomorrow, it's still saving it in yesterday's or today's, however you put it, right? So in order to get it to reset the folder, you either have to manually do it or you have to close the software and then it'll reset the folder. For that reason and one more, I recommend closing the software every day when you're done. The other reason is that it turns off the laser. If the software is off, even if you forget to turn this switch off, the laser will turn off. The laser is the most likely thing to wear out over time. So turning the laser off is something you want to do. So if you close the software every time, you're killing two birds with one stone, right? You're renaming the directory and you're turning off the laser. Okay? So when you're done imaging, when you're happy with your image, oh, by the way, so once you're imaging, if you see a region that you find interesting, you can draw a box in that region, right? Drag and release, right click. I like to do edit zoom because then it lets you pick the size. So I could do, for example, 2.5. Now it's going to zoom into that little region. This is a closed loop AFM. So if you tell it to move to a spot, it's going to move to exactly that spot, provided that you don't have thermal drift. If you have thermal drift, it might be off a little. Okay. Right. So once you're done imaging, you can hit withdraw, close the software. It's going to ask you, do you want to save changes? You do not want to save changes unless you're coming back the next day, in which case you probably shouldn't turn off the software, right? But yeah, generally no, because that's an Igor thing. Just to give you a heads up on that, Igor Pro is a software suite made by a company called Wavemetrics. We live within Igor Pro. We didn't write that code. We wrote what's called ZOPs, Extended Operational Procedures, and procedure files and calculation files and routines that all function within Igor. Igor will do presentation graphics, presentation quality graphics. It'll do a ridiculous amount of analysis on data. And so it was much easier for us to work within the Igor environment because we could just call ready-made functions rather than having to redesign everything. So you'll notice somewhere on the software, if you happen to dig around, you'll see there's something called the just Igor Pro. If you open that up without our software, it'll just be like a plotting program. But we live within Igor Pro, right? So when you exit and you say no, you're not saving, it means you're not saving Igor Pro file, right? Our software doesn't require any kind of saving. But again, to start up the software, you find this Igor Pro folder that says 15, double click, and then open it. All right, so let's take maybe a 5-minute break.